exist a bijection, which is a one-to-one correspondence, from the set of vertices in graph 1 to the set of vertices in graph 2. So we're going to have a set of vertices from each graph, and we want to be able to map them in a one-to-one correspondence. And there also will exist a bijection, which we can call a function g. So this above, we call this a function f. A function g that has the edges from the first graph to the second graph also matching. So we're going to use an adjacency matrix to make sure that happens. So notice you need corresponding vertices to have the same degree, because that'll be the number of edges coming in, or the number of edges that it is connected to. So these are a couple invariants. The invariants are what will not change in the graph if it is isomorphic. You need the same number of vertices, you need the same number of edges, and you need the same degree sequence. So if I'm looking to determine if G1 and G2 are isomorphic, this is where you should start. Do they have the same number of vertices? Yes, I have 1, 2, 3, 4, 5. Do they have the same number of edges? 1, 2, 3, 4, 5 on this side and 5 on this side? Yes. Do they have the same degree sequence? So like if you look at A, B, C, D, and E, we have degree 2 actually for all of them. And in G2, I also have degree 2. So I'm going to get the same degree sequence anyway, since all these vertices have degree 2. But just check if they're going to have the same degree sequence, though degree for each of those vertices. And if all three of these are true, then maybe you will have an isomorphism, but you still have to come up with the function, and you can look at the adjacency matrix to verify. If any of those three are not satisfied, then we don't go any further, then this is not going to be isomorphic. So for G1 and G2, what could an isomorphism be for these graphs? So I like to just think of, can I unravel the graph, one of these graphs? So think of this as a string with these vertices on it, these fixed balls there, that can you make it so it will match up with the graph of G1 if I unravel the graph G2 and make it connect? Can I get the star to become the pentagon? Because you know, when we do our graphs, we all do not graph them in the same way. So if I said, for example, you know, A, B, and I just have to get them to be connected. So I have A, B, C, D, and I need an E. Okay, so I'm looking at G1, and I see that A is connected to B, then B has to be connected to C, then C is connected to D, then D is connected to E, and then E is connected to A. So actually that graph G1 and the graph I just drew, I could unravel it, untangle it to get back G1. So those would be isomorphic. Now, how about with G2? Is that going to be the case? Well, it will be if I define this isomorphism correctly. So this is just one choice, so there could be different choices, but I'm going to decide to have my function map vertex A in graph 1 to the vertex 3 in graph 2. Let's let our function, which is our isomorphism, map B to, so if I'm going to start with this natural mapping, vertex in G1 to vertex in G2, what would be B? Okay, so here's B, A is connected to B. So I could say either that I can map it to a 1, or I could map it to a 5. But let me just kind of take this natural pattern to the left. So I'm going to take 1. And then what would f of C be? Okay, so once I am here at the 1, then I'm going down from B, so it has to connect from 1. So it's going to connect over to 4. So that one has to be a 4. What is your function going to map D to? So D is going to be that one-to-one correspondence now, so it goes from C to D. So remember, we're starting here at 4 now. So it's 4 to 2. And then what should E be mapped to? Okay, so from D to E. So that means that I need to now go from 2 to what it's connected to, which is 5. So that's one isomorphism that we can have that would make this graph look the same if we were to match these up. Excuse me. So two graphs are isomorphic if and only if for some ordering of their adjacency matrices they will be equal. So that's another, this is a nice thing, is I know they're going to be isomorphic if and only if I have some ordering. So there's some ordering of their adjacency matrices that will end up to be equal. So remember when we did our mapping, our isomorphism? So I used this isomorphism, 3, 1, 4, 2, and 5. Let me make sure that's the one I used, 3, 1, 4, 2, and 5. I went ahead and wrote down the vertices, the adjacency table for G1. So this is the adjacency table for G1. This is the adjacency table for G2. Okay, so the reason I did that is because now I want to show you how to look at the adjacency matrix, but using your isomorphism. So I'm going to have G sub 1. So pick on one of these, and I was mapping all of the vertices from G1. So I was going from A, B, C, D, E over to the vertices of G2. So I'm going to just take this adjacency matrix for G1. So these are all the vertices that are adjacent to each other, they're neighbors. This is the adjacency matrix. And then I'm going to make a G sub 2 matrix, but I'm not going to use this as is. So I'm not going to label it straight across as 1, 2, 3, 4, 5 on my adjacency matrix because they're not going to be exactly the same. So I'm trying to come up with some ordering. So what was my ordering? My ordering is my isomorphism. So notice I said I wanted A to correspond to the 3. So here's the A in this first column. I want it to correspond to 3. I want my B to correspond to 1. So remember we naturally put B over here in the second column. Well, I want it to correspond now to 1 for this vertex. And then just do the same thing. Then the 4, then the 2, then the 5. So I'm not putting 1, 2, 3, 4, 5 in order here because I'm trying to come up with a different order so that their adjacencies matrices will be the same. And now I read my adjacency table. You know, I still have to read this table because I don't want to change the graph. I just want to change the ordering in my matrix. So, for example, 3. What is adjacent to 3? So I come over to 3 and I see that 3 is adjacent to 1 and 5. So under the 1 column, I put a 1, and under the 5 column, I also put a 1. And you just finish out that table. So what about 1? 1 is adjacent to 3 and 4, so 3, and here's 4 over here. So just pay attention to where your vertices are now. 4 is adjacent to 1 and 2. 2 is adjacent to 4 and 5, I'm just checking. And 5 is adjacent to 2 and 3. So if you notice, the graph, the adjacency matrix for graph 1 in the newly reordered ordering of the adjacency matrix for G2 are the same. So we have G1 is isomorphic to G2, and our symbol that we use is the line with the tilde symbol on top. G1 is isomorphic to G2. Now let's look at another example using to determine if two graphs are isomorphic. Okay, so I have vertices. Yes, they're the same. The number of edges. So this has 1, 2, this one right here has 1, 2, 3, 4, 5, 6, 7 edges. And this has 1, 2, 3, 4, 5, 6, 7 edges. Okay, so that's good. And now I was looking at degrees. The degree of V sub 1, and that would be 2. The degree of V sub 2 is 1, 2, 3, 4. The degree of V sub 3 is 2. The degree of V sub 4 is 3. And the degree of V sub 5 is 1, 2, 3. Okay, and then I want to look and say, do they have the same degree sequence? So if I could, I might want to shift this a little bit and start, for example, here, like at the 2. So if I had, and I'm just going to move that one down here. So if I had 2, 3, so I could do 2, 3, 3, 3, and then I'm going to start and look at this one, and this one is going to be a 2, 4, or can I get that? No, see, either way, if I shifted it this way or leave it this way, 2, 4, 2, 3, 3, or I could have had a 2, 3, 3, 2, 4 if I started at that value. So 2, 3, 3, and I forgot a 3. Okay. So I know that on V sub 2, for example, this degree is a 4. That degree is a 4. It's not the same degree sequence. So no, this would not be an isomorphism on this example. So what we first check, remember, is do these two graphs have the same number of vertices? Yes, 5. Do they have the same number of edges? Yes, we do have the same number of edges here. And what about the degree sequence? Can we come up with the same degree sequence? So for this one, what I can do is I need to label the degrees here. So maybe if I can just write down that this has, count the number of edges that are incident with the vertex. So degree 3 here, U2, just count them up, 1, 2, 3, 4. Degree 3, U4 is degree 1, 2, 3, 4. And this is degree 2. And then do the same thing for V sub 1. Count them. Okay. So now that we have these, what I can do is I can start and say I'm going to have my sequence start at U sub 1. So for U sub 1, I know that's degree 3. So what's the degree sequence? From U sub 1, I'm going to just go to U sub 2. That's a degree 4. And I'm just going to keep track on top here. U sub 3 is what it connects next to, degree 2. U sub 4 connects to a degree 4. Vertex, U sub 5 is degree 3. Okay, so I've kept track of the connection here from U sub 1 to U sub 2, U sub 3 to U sub 4, and U sub 5. So now what I can do is over here for V, I'm going to start with the same degree that U sub 1 starts with. So U sub 1 starts with degree 3, so I'm going to start here with V sub 1. And then from degree 3, I need to go to a degree 4 in the right-hand side graph. So what does V sub 1 connect to that has, which vertex has degree 4 here? Well, I can go over to a V sub 3. So let's make that one our next choice. So this will be an option for our isomorphism here. And then from V sub 3, I need a degree 2. So it connects over to V sub 2, which is degree 2. And then V sub 2 needs to connect to a degree 4, which it does here at V sub 5. And then I need to connect to a degree 3. So a degree 3, which I haven't used, is V sub 4. Good, connects. So I do have the same degree sequence now that I've written it this way. So what we're going to do for isomorphism is just match these vertices. That's what our mapping is going to be. And so if you looked at the adjacency matrix, they will be the same for the graph U using this in your rows and your columns of the adjacency matrix. And this is what we'll have to use in our rows and our columns for the adjacency matrix, is that reordering. So our isomorphism is f of U1. So this means the isomorphism, the function, is going to map U sub 1. So we're going to take vertex U sub 1 on the left side and make it matched up with V sub 1 vertex on the right side. And then what else? It's going to take U sub 2 and it's going to map it to V sub 3, U sub 3, is V sub 2, U sub 4 is V sub 5, and I've run out of room, but U sub 5 will be V sub 4. So this is a choice of an isomorphism so that we do have the same number of vertices, of course, the same number of edges, and we do get back the same degree sequence.